This will be another assignment that you really want to do on your own, but as you need to, you can come back and check this out and check your work. If you get completely stuck, you can always check here and see how to do it. So the very first thing is the formula, and a lot of times I hear this referred to as PERT, kind of looks like that. That is the continuous growth rate formula for, at least for money. And here I said to use C as your initial amount. So it'll be CERT. That's what we usually refer to it as. So that is going to be your continuous growth formula for all other situations that don't involve money, with the only C being different than P. It's really the only difference. So these couple examples, you're going to look for some common things happening. Just kind of plug them in and go, but again, you'll look for some common things and you'll eventually derive some new formulas that'll kind of help you, but you don't have to memorize them. You can always derive them if you need to. So suppose $2,000 is invested at 2% continuous interest. How long does it take to double? All right. So $2,000 is invested, and e to the rate's going to be 0.02. Make sure you turn your rate into a decimal, your percent to a decimal. And the amount would be the ending amount. So if it's going to double, it's going to be worth 4,000. That's something you'll see pretty soon right here. Anytime you double something and you divide off that first part, you end up with 2 equals. So that's something that'll keep happening. You can kind of do a shortcut there if you want. If something's going to double, 2 equals e to the rate times time. All right, well, our variable is an exponent, so that means logarithms are going to come into play. So let's take a log of both sides. Log of e makes that go away. And finally divide by 0.02 on both sides, and that'll give us our time. And you can always leave it that way as an exact solution. I got 34.6 roughly, so I'm gonna call that about 35 years. With money, we're not looking for super precise, I wouldn't say as far as time with money. We'll, unless I ask for months or something like that. So about 35 years, it's good for that. Okay, next one, we have continuous interest. We have an initial investment of $4,500, and it's going to double in 26 years. So I don't know the rate, but I do know the time is 26 years. It's going to double, so it'll be worth $99,000 at that point. So again, if you divide by the 4,500, you'll get 2 equals e to the 26r. I'm just reversing those so it looks a little nicer. And we'll take log of both sides. So log of e makes that go away. So log of 2 divided by 26 is your rate. And I got about 2.67%. All right, which means I had about 0.0267 and some other stuff. But I turned it into a percent to make it a rate. Okay, radioactive isotope, half-life of 3,431 years. That means if I start with 10 kilograms, then I'll have 5 kilograms in this many years. What's the rate of decay? So I'm looking for rate. Okay, that's the thing I don't know. So be careful with the order. This one's a little bit different. It's a half-life, it's deteriorating. So the amount I will have in time is 5 kilograms. The amount I start with is 10. And let's see, e to the, well, I don't know the rate, but I do know it's 3431 years. And what I'll hear oftentimes is, this doesn't look like what we did in chemistry. It's like a different formula. But if you look close enough and you work with them enough, you'll see that we're just rearranging things. We're starting with our formulas we've derived, and we're just rearranging things. I promise you, they're the same thing as chemistry. Science and math are the same thing. So if you think they're different, just keep messing with them. I think you'll see they're the same thing. So 5 divided by 10 is a half. So 1/2 is e to the 3431r. We'll want to take log of both sides because our variable is an exponent. So log 1/2 is, and that log of e is going to go away, 3431r. So divide by 3431, and our rate, it's negative, so don't be thrown off by that. And it's going to come up in scientific notation in the calculator, and that's okay. What I usually do is write it in scientific notation, or I'm sorry, write it in the normal form. So I put it was to the e to the -4th power. So I moved my decimal 4 places, and 3 zeros in my 2. So negative 0.02%. I'll go ahead and make it a percent too. So the things that I'm hoping you're seeing happen on 2 and 3, your rate, if we want to, I'll just kind of come down underneath here. If something's going to double, then you're going to end up with 2 times e to the rt every time. And we're going to take log of 2 to make the e go away, which means we'll divide by t to get r. So log 2 over t, that's your rate. And if it's a half-life, it's log of a half over t, that's your r. So those are the 2 things that will hopefully you kind of caught on to those as you were going. I don't really call them new formulas, but they're kind of useful shortcuts. You can always derive those if you have to, though. All right, this one is, it was one of the examples in the book. It's carbon-14 is a naturally occurring radioactive isotope of carbon atom, makes up all living things on Earth. By measuring the amount of carbon-14 in a once living plant or animal, scientists can estimate how old the sample is. So it's about carbon dating. The half-life of carbon-14 is 5,700 years. The 14 is just a name, so don't throw 14 in your math. It takes 5,700 years for half of the carbon that was there to break down and disappear. So suppose an archaeologist discovers a settlement and finds an old fire pit with charcoal containing 30% of the carbon-14 of a normal charcoal. So basically, back when this was new, it would have had 100% of the carbon-14 we would expect, and now it has 30% of that. So how old, that's going to be in time, how old is this charcoal based on carbon dating? Okay, so this one, you got to kind of think about the setup. So it's going to have 30% of what it started with. You don't have to worry about whether you make this a decimal or not. Either way, it's going to wash out when you do your division. You start with 100%. And here's where you got to be really careful. 5,700 years is the half-life. That's how long it takes for half of the amount of carbon to break down. What I'm looking for is how old is this charcoal. So my time is not 5,700 years. My time is the age of this charcoal. I also don't know the rate. So we've got 2 things we don't know. We don't know the rate or the time. Probably should have put those by the other order, but I'm sure you're okay with that. So here's where the other part comes in. Now we can set up, let me do it a couple ways. So if it's a half-life, I'll have 50% of what I started with after 5,700 years times whatever rate that is. Or if you just kind of use a shortcut, rate is log of a half divided by that time. And if you solve this, you'll get to here, but that's that shortcut we derived on the other side. So if I do that, I'm getting about, let's see, negative 0. Log of a half divided by 5,700. So that would be 0.0001216. I'm going to leave it that way. I'm not going to make it a percent. And what I encourage you to do is when you put this back in the calculator, just pull that back up and I'll show you what I mean. So over here, if we divide by 100, then that's 0.3. 0.3 to make it proper. And we'll say RT, just put in the right order. So log of 0.3, and that makes e go away if I rewrite it as a logarithm or take log of both sides. And I do know the rate, but what I'm going to do is leave it as r for now. R is this number over here, but it's just so much to write. It's just easier to leave r for now. So log 0.3 divided by, and I'm just going to go up and highlight that. It's just way easier. So about 9,900 years. And that's the way I'm going to leave it. I'm going to say about 9,900 years. You can get precise if you want to, but carbon dating, that's pretty darn close, I believe. Okay, last thing is scatter plots. Just matching data. At this point, you want to really make sure you're looking through all the different options when you go to create your equation. So I'll tell you what I mean when I get there. So let me recap this process. You go to Stat, Edit, and then you put your numbers in your list. Now I've got both of these preloaded, but list 1 and list 2, that's this first chart right here. So first, just to see it, you go to second and y equals. Make sure this is on. Make sure you got scatter plot chosen. Make sure list 1 and list 2 are chosen. The mark, you can make whatever you want. To see it, we do zoom, and I go down to option 9, which is stat. And that'll bring up the graph. Now I don't want to see that yet. I'm going to show y'all how we get here. So I'm going to clear these out for you because I want y'all to see how I get here. So there, when I do the graph, that's what I get. So a couple things that it may or may not be. I don't think it's going to be linear. I don't think we're going to line through this and have a good fit. It looks curved to me. So a couple things I'm seeing is maybe it could be quadratic. And the more data you have, the better, just like everything else in real life. So if it's quadratic, it's going to go back up on this backside. If I have enough data to know it doesn't go back up, that it starts off flat and then kind of goes up for a while, then that's probably exponential. So you can try either one. For this, since we're talking about logs and exponentials, I'm going to assume, I don't know, I shouldn't assume, but I'm going to assume this is exponential. Anyway, there's quadratic, cubic, quartic, which is like x to the 4th. I don't really know. I've never used the 8 option. So if y'all have a good use for you, let me know. There's your natural log regression, exponential, power, logistic, that's something we'll talk about in a second, sine regression, and then manual fit I don't think we'll ever use. So exponential is what I'm going to try. I want to make sure it's list 1 and list 2. Now, so here's a little shortcut you can use. If you want to put this in y equals automatically so that you don't have to type it all in there, so go down where it says store equation, hit vars for variables. All right, we want to put it in y equals, so we go to y variables. Vars sounds more fun. Go to y1 or whichever one you want to put it in. I don't have anything in y1, so I'm going to put it there. And it should say y1 now. Okay, and then when you calculate it, it's automatically going to put it there for you. So to write this one out as an equation, A is 0.3, we'll go with 0.39, should be good enough, times 1.46 to the x power. So that'll be our exponential equation. If you want to see how good of a fit you have, now if you just hit graph, it should already be stored for you. And we'll see how close it is. And we'll tell you quadratic's a pretty good fit too if you tried that one. But again, we just need to have more data to know, does it stay pretty flat here, or does it go back up? If it goes up, it's quadratic. If it stays flat, it's exponential. So that's kind of the tough parts about these. All right, here's the next one. I've already got this preloaded too. I put it in. So if I go stat edit, now for you, you're probably going to want to go up and hit clear and come back down. I've already got it preloaded. Let me show you this just in case you messed this up. Suppose you went up here and hit delete because that seemed like a smart thing to do because you wanted to delete your numbers. Well, it actually deletes the list. The only way to get it back is go to stat, go to setup editor, which is number 5, hit enter, and it brings it back for you. Everything should show back up. All right, I've already got them in list 3 and 4, so I'm going to graph those. So when I go to second y equals to turn the scatter plot on, I'm going to pick list 3 and list 4. The way I'm doing that, second and 1, 2, 3 through 6, those are your list numbers. You can see L1 through L6 up there. All right, so I am going to also go to y equals. I don't really want to see that equation on here. And if I just graph right now, I'm going to see the last window. So I'm going to do zoom 9 again. So I see this window. Now, there's a special type I want you to be doing on here. It looks kind of like exponential, except this dot seems to be kind of leveling back out. This is, always when you do population, you want to use this model. It looks like it's kind of going up sharply and then leveling back out. So this is what we would call a logistic model. It's what populations follow because there's usually some barrier to growth. You think about human population, the earth can only hold so many people, or really any animal. So you'll have really fast growth for a while, but then it's going to slow down as you approach that upper limit of what the environment can handle. So we're going to pick logistic. So I'm going to go to stat calc, and we'll go down till I see logistic. And I'm going to change this to list 3 and list 4. You probably don't need to do this if you're keeping in list 1 and 2. Store regression equation, I'm going to go to variables again. Here, let me put it up there so you can see it. So I went to variables and y variables. I want to choose function. And I'm going to make this y2 because I've already got something in y1. And there we go, we'll calculate. So the equation, this one might take a little while. These are pretty massive. C's on top, so 16.7, 1 plus A, which is 31.4, times e to the negative b, so about negative 0.8. I'm just rounding to a decimal place on these to the t. That's probably good enough. You can always round more if you want more precision. And then we'll hit graph just to see if it's a pretty close fit. And it looks like it's hitting most of them pretty good. So logistic again, starts off pretty slow, goes up fast, and then kind of levels off at some upper limit.